So today I was going to talk about the gas laws for chemistry. And gases, they have their own set of rules. They behave according to their own set of rules. And when I say gas, I'm talking about, anything like in the air or in a gaseous state. There's helium gas, there's hydrogen gas, and when something's in its gaseous state, it behaves according to its own set of rules. Now, there's these three guys, Boyle, Charles, and Avogadro. They each individually were playing around with gas and found three things, one each, about the laws of gas. Boyle found that volume affects the pressure of a gas in a container. So if you put a gas in a container, like if you fill up a balloon with helium, then that's going to have a certain amount of pressure to it depending on how much helium you put into the balloon and depending on how big the balloon is. So volume affects the pressure and vice versa. The pressure affects the volume if the container is flexible, if it's like a balloon that can get bigger or smaller. Charles discovered something else. He discovered that the temperature affects the volume of the gas and vice versa. So if you heat up the helium that's in the balloon, that's going to expand the balloon or contract the balloon depending on if you heat it up or cool it off. And then there's Avogadro, which you might know Avogadro from Avogadro's number. It's the same guy. He just has a lot of stuff named after him. So this doesn't have anything to do with Avogadro's number. This is just this was discovered by the same guy, so it's called Avogadro's law. But he discovered that the moles of gas, the amount of gas you put in, is going to affect the volume. Well, this might seem very obvious because if you put more moles of gas of helium into the balloon's going to get bigger, right? So this is just a pretty obvious one to us, but at the time it was a big discovery for Avogadro to actually just state the obvious in a mathematical format. So when we're dealing with Boyle, the volume affects the pressure and vice versa. That gives us this mathematical equation, and the P stands for pressure and the V stands for volume. So if we start out at a starting point with a certain amount of pressure in a certain amount of volume, but then we increase the pressure or increase the volume, it's going to affect the other thing. If we increase the pressure, it's going to affect the volume, or if we increase the volume, it's going to affect the pressure. Now Charles's law is this mathematical formula, and the volume is V, and the temperature is T, and the temperature needs to be in kelvins to make this mathematical equation work. So if we start out at a certain volume, the balloon starts out at a certain size, and we start out at, like room temperature, or a certain temperature, and then we increase the volume or we increase the temperature. If we increase the volume of the gas or we increase the temperature, that's going to affect the other thing. So if we increase the volume, it's going to affect the temperature. If we increase the temperature, it's going to affect the volume. And then Avogadro's law gives us this mathematical formula where if we increase the volume of something, that's going to affect the number of moles that's there. If we increase the moles of the gas, that's going to affect the volume of the gas. Now, something I want to point out to you, each one of these, if you haven't noticed, each one of these laws has to do with the volume of the gas. That's what these three laws have in common. It's all about the volume. And so Boyle's law is about pressure and volume interacting. Charles's law is about temperature and volume interacting, and Avogadro's law is about the moles of gas, the amount of gas, and the volume interacting. So in Boyle's law, the volume, as all of these laws have to do with volume, but with Boyle's law, we're talking about volume and pressure. The volume affects the pressure, and the pressure affects the volume. So you might ask, well, how do they affect each other? And they affect each other inversely. Inversely. And that means when one goes down, the other one goes up. And when one goes up, the other one goes down. So they're like the opposites of each other. So if pressure goes up, then volume goes down. If volume goes up, then pressure goes down. And so that gives us this mathematical equation that at the beginning, when you first start out, you have your contents, your gas under a certain amount of pressure, and it's at a certain volume. So the balloon is a certain size that you put the helium into, and the helium inside the balloon gives a certain amount of pressure to it. But then if you change either the pressure or the volume, then the other one is going to change. So if you take that same amount of helium that's in that balloon and you put it into a smaller container, you've decreased the volume. So that's going to increase the pressure. So this is P1 when we have the little 1 after the P and the V. This is going to be your starting point. See, 1 is going to be the starting. And then P2 and V2 is going to be your ending after you've changed containers, after you've put it in a different container, a smaller or a larger container. So again, say you put, here's your initial P1 and V1. So we put, here's your balloon, and we put a certain amount of helium in this balloon, and this balloon takes up a certain amount of volume. So this takes up a certain amount of volume. So we're going to call this V1. And this gives us a certain amount of pressure because there's helium gas in the balloon. So this gives us a certain amount of pressure. And we're going to call this P1. But then we take that same amount of helium and we put it into a much larger balloon. So now there's that same amount of helium, but it's in a much larger balloon. So the much larger balloon is going to be a larger volume, and we're going to call that V2, the second volume, or the volume in the second container, and that's going to give us a pressure, a lower pressure, because volume and pressure affect each other inversely. When one goes up, the other goes down. So we gave it a bigger volume, so the volume went up, so the pressure is going to go down, and that new pressure is going to be called P2. Now with Charles's law is also about the volume, because remember all these laws are about the volume of the gas, but Charles's law is about the temperature and the volume of the gas affecting each other. So how do they affect each other? Well, unlike with Boyle's law, when the volume went up, the pressure went down. When the pressure went up, the volume went down. But in Charles's law, Charles found that the temperature and the volume will both go up or both go down. So when one goes up, the other also goes up. If one goes down, the other goes down. And this gives us this mathematical equation: the volume over the temperature, the volume divided by the temperature. So the volume divided by the temperature, at first, when you first have it, because look, there's the little ones after the V and the T. If you change the volume or if you change the temperature, the other one's going to change. So this is the changed amounts, because it has the little 2 after it. So the V1 over T1 is the gas at a certain temperature, like let's say this is room temperature, just for an example. And then if you increase or decrease the temperature, now you have a new temperature, which is going to be T2, and that's going to give us a new volume, which is going to be V2. So here's our starting point, V1 over T1. So if we have our balloon and it's filled with a certain amount of helium, and the volume is a certain size, the helium fills up this balloon to a certain size. So this is going to be V1, a specific volume, and the T1, let's just say, for example, it's going to be at room temperature. Room temp. But then we take that same amount of helium in that same balloon, but we heat it up. So we're going to build a little fire underneath. Here's my fire. This is flames. So we're going to build a fire underneath, and it's going to increase the temperature. So this is going to be T2. This is going to be your second temperature. That is going to increase the volume. So the balloon is going to get bigger. Even though there's the same amount of helium in there, since it's hotter, the helium is going to be bouncing around in there, and it's going to take up a lot more space. So this is going to increase the volume, and we're going to call that V2, your second volume, because your first volume was what you started with, and so your second volume was what you ended up with after you increased the temperature. Now, Avogadro's law, again, this is dealing with volume. All of these laws are dealing with volume of the gas. Avogadro's law deals with how the volume of the gas and the amount of the gas affects each other. And so in the amount of gas, we're dealing with the moles of the gas. So how do they affect each other? How does the moles and the volume affect each other? Well, just like in Charles' law, Avogadro found that when one goes up, the other goes up. So they affect each other in the same way. When one goes up, the other goes up. When one goes down, the other goes down. So if you increase the moles, you're going to increase the volume. And if you decrease the amount of gas, the moles of the gas, you're going to decrease the volume. And this gives us this mathematical formula. The first volume, or the volume you start with, because it's got the 1 after it, divided by the number of moles. N stands for number of moles, so N, number, and then you increase the number of moles of gas. You put more gas in there, you put more helium in there. That's going to increase the volume. So let's take a look at this example. So if we start out with a certain amount of gas in a certain volume, so here's our balloon, and our balloon is a certain volume. Our balloon has a certain volume to it, and we have a certain amount of helium in there. So the volume is going to be our V1. This is what we start with, the volume we start with, and the moles of helium is going to be our N1. But then we add more helium to it. We add more moles to it. So if we increase the moles, the number of moles of helium, that's going to be N2, our second amount of helium. And what is it going to do? It's going to, if we put more, and this might sound obvious, but if we put more helium into the balloon's going to get bigger because there's more helium going into it. So the bigger balloon is going to be our second volume, our new volume, the volume that we end up with as a result of adding more helium to it. So this is kind of obvious. If you put more helium into a balloon, the balloon's going to get bigger. And that's all Avogadro's law means. Now, one more thing that I should add about these gas laws is that the pressure, you just have to remember that the pressure is going to be calculated in atmospheres, in ATMs. The volume is going to be calculated in milliliters. The amount, the N, is going to be calculated in the number of moles of the gas. And the temperature is going to be calculated in kelvins. So whenever you're doing these problems, you have to make sure that you have your pressure in ATMs, your volume in milliliters, your amount of gas in moles, not grams, and your temperature in kelvins, not Celsius. So do you remember how to convert Celsius to kelvins? You should make sure that you have that memorized so you can quickly convert Celsius to kelvins. Okay, so let's take our first practice problem. A gas occupies 12.8 liters at 760 torr. If the pressure is increased to 1520 torr, what is the volume of the gas? So first, let's read this problem again and look for what they're asking. What are they asking? So a gas occupies 12.8 liters at 760 torr. If the pressure is increased to 1,520 torr, what is the volume of the gas? So they're asking, what is the volume of the gas? So we already have one volume. They gave us the starting point volume. It's saying a gas occupies 12.8 liters. So this is going to be your starting volume. So 12.8 liters is your starting volume. So your starting volume is going to be V1. And there's a 1 after the V to show that that's where you started from, your starting volume. and it asks what is the volume of the gas if you increase the pressure. So they're asking for a new volume of the gas. If you increase the pressure, if you change the pressure, then there's a new volume that's created. So they're going to ask, what is the new volume of the gas? And so that's going to be your V2. Now what else do we have to work with here? It says a gas occupies 12.8 liters at 760 torr. Well, torr is a unit of pressure, right? So 760 torr is going to be the pressure when the volume is occupying 12.8 liters. So when the volume is occupying 12.8 liters, that's V1, right? So 760 torr is going to be your starting pressure, which is going to be P1. So this pressure, this 760 torr, is going to be the pressure when the volume is 12.8 liters. But then the question goes on, if the pressure is increased to 1520 torr, what is the volume of the gas? So the 1520 torr is going to be your new pressure. And just like your new volume is going to be labeled V2, we're going to call this new pressure P2. So now we have a V1, we have a question mark for V2, and we have our P1, and we have our P2. So which gas law should we use? Which mathematical formula should we use to calculate this? So we are dealing with volume and pressure, which is going to be Boyle's law, the one with P1 V1 equals P2 V2. Now one other thing I want to mention is that it's best if we keep everything in milliliters and atmospheres for volume and pressure. So 12.8 liters is going to be 12,800 milliliters. And 760 torr is going to be just 1 atmosphere. So if 760 torr is 1 atmosphere, 1,520 torr is going to be 2 atmospheres. So now we have 12,800 milliliters is our V1. Our V2 is what we're solving for, is unknown. Our starting pressure, our P1, is 1 atmosphere, and our new pressure is 2 atmospheres. Now, so we know that we need to use this formula because it's the only formula that has pressure and volume in it. So we need P1 times V1 equals P2 times V2. P1 is going to be 1 atmosphere. So we're going to have 1 atmosphere times V1, which is 12,800 milliliters. And that's going to equal P2, which is 2 atmospheres, times V2, which that's what it's asking for, so times question mark, or times X. We're going to use an X. So this question mark is the same thing as just putting an X there. So let's just calculate this. So how do we go about algebraically solving this? Well, first we can multiply this 1 atmosphere times 12,800 milliliters. So that's going to give us 12,800, because 1 times 12,800 is 12,800. And then on the other side, we have this 2 times x. So that's going to give us 2x. But we need to get this x all by itself on one side of the equal sign. So how do we do that? We divide both sides by 2, and these 2's cancel each other out. And this 12,800 divided by 2 is going to equal 6,400. So you're going to end up with 6,400 equals x. And what is our x? Our x is our second volume, our new volume. And volume is in milliliters, right? So that's 6,400 milliliters is going to be our new volume. And answer this question, what is the volume of the gas if the pressure is increased to 1520 torr? So as you can see, the volume went down. It went from 12,800 milliliters down to 6,400 milliliters when we increased the pressure from 1 atmospheres to 2 atmospheres. So let's try another problem. Calculate the decrease in temperature when 2.00 liters of a gas at 21 degrees Celsius is compressed to 1.00 liters. So what is this question asking? It says calculate the decrease in temperature. So how much the temperature goes down. So this decrease in temperature when 2.00 liters of a gas at 21 degrees Celsius is compressed to 1.00 liters. So we have 2.00 liters of a gas, so that's going to be your volume. So 2.00 liters is going to be your starting volume, so that's V1. And it says when 2.00 liters of a gas at 21 degrees Celsius. So when the volume, the V1, when we have V1 at 2.00 liters, the temperature is 21 degrees Celsius. So that's going to be our starting temperature. So when our starting volume is 2.00 liters, our starting temperature is going to be 21 degrees Celsius. And then it says is compressed to 1.00 liters. Well, so this is going to be your new volume. So if you have that balloon with helium in it, and the volume is 2.00 liters, but then we take that same amount of helium and we put it into a smaller balloon when the balloon is only 1.00 liters, then we want to know the temperature. So when we compress it to 1.00 liters, that's going to be our new volume. So that's going to be V2. And our new temperature, if our new volume is 1.00 liters, is what we need to calculate. So that's going to be our question mark. So which law should we use? Which mathematical formula should we use to figure this out? Well, they all deal with volume. So each law deals with volume. But this problem in particular is dealing with temperature, the change in temperature. So we're going to use the law, the mathematical formula that includes the temperature in it, which is going to be this middle one, this Charles's law. So V1 over T1 equals V2 over T2. But before we plug those numbers in, we need to convert these into usable format. So 2.00 liters for our V1 is going to be 2,000 milliliters. And 21 degrees Celsius for our temperature, we need to convert that to kelvins. So do you remember how to convert temperature to kelvins? To convert temperature Celsius to kelvins, we just add 273.15. So that's going to give us 294.15 kelvins is our T1. And then our milliliters for V2 is going to be 1,000. So now we can take these numbers, now that they're converted, we can take these numbers and plug them in. So V1 over T1 equals V2 over T2. So our V1 is 2,000 milliliters over T1, which is 294.15 kelvins. And that's going to equal our V2, which is 1,000 milliliters, over question mark. So we're going to put an X there. Now, so we have an interesting problem here because we have a V1 over T1 that we know what it is equals V2 over question mark over X because we don't know what T2 is going to be, the temperature. So we need to get this X all by itself on one side of the equal sign. So if we cross multiply the 2,000 times X and the 294.15 times 1,000, then we're going to get 2,000x equals 294,150, 294,150. Then we can take that 2,000 because we have 2,000x and we need to get the x by itself. So we have to divide both sides of the equation by 2,000. So this cancels each other out, the 2,000s over here on the x, just leaving the x all by itself. And 294,150 divided by 2,000 is x equals 147.075. And that's temperature, so that's in kelvins. So you see the temperature went from 294.15 down to 147.075 when the volume went from 2,000 milliliters down to 1,000 milliliters. Now, but that's not the end of the story, because this question was calculate the decrease in temperature. It didn't say what is T2, what's the new temperature. It asks you for the decrease in temperature, how much the temperature went down. So if we started out at 294.15 kelvins and we ended up with 147.075 kelvins, then we need to subtract that to find how much the temperature went down. So that's going to be 147.075. It went down exactly by half. So that's going to be, the decrease in temperature is going to be 147.075 kelvins. Okay, so another practice problem says 5.00 liters of a gas is known to contain 0.965 moles. If the amount of gas is increased to 1.80 moles, what new volume will result? So what is this question asking? So the question is asking what new volume will result? What new volume will result if the amount of gas is increased to 1.80 moles. So what new volume will result? So our new volume, that would be V2, the new volume, is going to be the question mark. So what would be the first volume? What would be volume 1, V1? V1 would be, at the beginning of this question, we started out with 5.00 liters of a gas. So that's going to be our V1. And it says 5.00 liters of a gas is known to contain 0.965 moles. So this is going to be the amount of gas. So the amount of gas, the number of moles, is our number, or it's our letter N. So our starting out amount, N1, is going to be 0.965 moles. And then it says if the amount of gas is increased to 1.80 moles, so that's going to be our new amount, our N2. And let's go ahead and take this volume while we're at it, this 5.00 liters, and we're just going to convert that to milliliters right off the bat. So now we have milliliters and we have moles. So which math formula of the gas laws should we use? Well, we have volume, but all the gas laws are about volume. So what's the other thing that we have, the other piece of information? We have the N, the amount of gas, the number of moles. So that's going to be Avogadro's law over here. V1 divided by N1 equals V2 divided by N2. So our V1 is 5,000 milliliters divided by our N1, which is 0.965 moles, and that's going to equal our V2, which we don't know what our V2 is, that's the question mark, so we're going to put an X there, over N2, which is 1.80 moles. So first we can go ahead and divide the 5,000 divided by 0.965 moles. And we get 5,181.3471502.591 equals X over 1.80 moles. Now we need to get this X all by itself on the equals, on one side of the equal sign. So we do that by multiplying both sides by this 1.80, which cancels out the 1.80 underneath the X, and we go 1.80 times this long number, and we get 9,326.42487 equals X. So this X, what does this X stand for? This X stands for our new volume, and that's going to be in milliliters. So we're going to have 9,326.42487 milliliters is our new volume. And if we round to 3 significant figures, that's going to give us 9,330 milliliters, or 9.33 times 10 to the third milliliters. And that's going to be our new volume.